In my earlier video, I had discussed what is the similar matrices. I had seen two matrices represent the same linear operator if the matrices are similar. And I had seen the definition of similar matrices is if A is similar to B, that means there exists an invertible matrix P such that B equal to P inverse AP. That imply AP equal to PB. And also I had seen the properties of similar matrices are if A and B are similar, then always their determinant equal, their trace equal, they have same characteristic polynomial, same eigenvalue, but eigenvector corresponding to eigenvalue for similar matrices may be different. In fact, if X is eigenvector corresponding to eigenvalue lambda of a matrix A, then P inverse X will be the eigenvector corresponding to eigenvalue lambda for the matrix B. And today's goal of this lecture is diagonalization of a matrix. At first, I will tell you, please pay attention in today's video because diagonalization of a matrix is a very important for any competitive exam. At first, say, what is the diagonalization of a matrix? A square matrix A is said to be diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. That means A is similar to a diagonal matrix. This is the concept of diagonalization of a matrix. Okay? OL. That means a linear operator T is said to be diagonalizable when the matrix representation of T is similar to the diagonal matrices. That means T is similar to the diagonal matrices. That means by definition there exists an invertible matrix P such that T equal to PDP inverse, and the idea of diagonalizability is let T be a linear operator on the finite dimensional vector space V. Then we say that T is diagonalizable if there exists a basis for the vector space V such that each vector of which be the eigenvector of this linear operator. That means there exists a basis u1, u2, un of the vector space V for which T u1 equal to lambda 1 u1, T u2 equal to lambda 2 u2, and this would be continue. Then T un would be lambda n un. Then this T represented by a diagonal matrix D. That means since every linear operator represents a matrix, so obviously by definition A is similar to diagonal matrix. That means A is similar to diagonal D1, D2, Dn. So by definition of similar matrix, there exists an invertible matrix P such that AP equal to PD, that imply A equal to PD P inverse. And we all of us know for similar matrices the eigenvalue are same, since this linear transformation represents the matrix A whose eigenvalue are lambda 1, lambda 2, lambda n. That means the eigenvalue of diagonal matrix also lambda 1, lambda 2 up to lambda n. Are you getting? I hope my all viewers have understood what is the diagonalizability of linear operator and when a matrix be diagonalizable. And the idea A equal to PDP inverse is such type if we multiply both sides by P inverse times AP, then this would be P inverse times P times D times P inverse P. Just omit P inverse P in both sides. Then this would be P inverse AP equal to diagonal matrix D, where P matrix is said to be diagonalize the matrix A. And this process will be work when A has only one eigenvalue, or if there exists multiple eigenvalue, but for each eigenvalue there exists linearly independent eigenvector. Because the diagonal matrix D is made up by the eigenvalue of A and P is made up by the eigenvector of A. Are you getting? So, to find a matrix is diagonalizable or not, for this consider AB an n cross n matrix. Then A is diagonalizable if A has n linearly independent eigenvectors, or if an n cross n matrix A has n distinct eigenvalues, then A is diagonalizable. That means if A has n distinct eigenvalues, then we can tell obviously A is diagonalizable. Or if A has multiple eigenvalues, but if there exist for each eigenvalues n linearly independent eigenvectors, then we can tell also A is diagonalizable. As for example, diagonalize the matrix A equal to 5 0 0 0 5 0 1 4 minus 3. Since this is the lower triangular matrix, so obviously the eigenvalue are 5 5 minus 3, and for lambda equal to 5, the eigenvector are, this is A minus 5i, that means 5 minus lambda 0, 0 5 minus lambda 0, 1 4 minus 3 minus lambda equal to 0 0 0 vector. And this is, since for lambda equal to 5, now put the value of lambda, then this would be 0 0 0 0 0 0 1 4 minus 8, here 0. And notice, if we write extends the row, if we extend 1 4 minus 8 0 0 0 0 0 0 equal to 0 0 0, notice this is the augmented matrix of this matrix, and here 1 is a pivot, and this vector x2 and x3 be the free vector. That means, that implies x1 plus 4x2 minus 8x3 equal to 0. That means x1 equal to minus 4x2 plus 8x3, and consider the vector as x1, x2, x3. Now put the value of x1 here. This would be minus 4x2 plus 8x3. This is x2, x3. That means this is equal to x2 times minus 4 1 0 plus x3 times 8 0 1. This is the eigenvector minus 4 1 0 and 8 0 1. This is the eigenvector corresponding to eigenvalue lambda. Okay, lambda equal to 5. Since other eigenvalue is lambda equal to minus 3, so for lambda equal to minus 3, a minus 3i equal to 5 minus lambda 0 0 0 5 minus lambda 0 1 4 minus 3 minus lambda equal to 0 0 0. Now put the value similarly lambda equal to minus 3, then this would be 8 0 0 0 8 0 1 4 0 equal to 0 0 0. That means this is equivalent to 1 0 0 0 0 1 0 0 1 4 0. And if we reduce R3 dash equal to R3 minus R1, then third row would be 0 4 0. Then our original matrix after reducing 1 0 0 0 1 0 0 0 0. And here x1 and x2 are pivot and x3 are free variable. And since x3 is free variable, so consider x3 equal to c, and from this expression x1 equal to 0 and x2 equal to 0. Therefore, the vector would be x1, x2, x3 would be 0 0 c, that means c times 0 0 1. That means for the eigenvalue lambda equal to 3, the eigenvector would be 0 0 1. This is the eigenvector. I have got these three linearly independent eigenvector for lambda equal to 5 and lambda equal to 3. Therefore, the matrix P would be minus 4 1 0, 8 0 1 and 0 0 1. And D would be, since the eigenvector is 5 0 0 0 5 0 0 0 3. Therefore, by the diagonalized theorem, we can tell PDP inverse would be the given matrix A. So, we can tell given matrix A would be diagonalizable. Are you getting how we have to find OL? Notice, eigenvalue not distinct, but eigenvector are three linearly independent eigenvector. By this theorem, we can tell since A has n linearly independent eigenvectors, so obviously the matrix A is diagonalizable. Now I will see how we will find is the matrix is diagonalizable or not. What is the condition? Geometric multiplicity. We all of us know what is the geometric multiplicity. In my previous video, I had discussed geometric multiplicity of an eigenvalue lambda is number of linearly independent eigenvectors associated with lambda. That means this is actually dimension of null space of A minus lambda I. Therefore, if R is the rank of A minus lambda I, then number of linearly independent eigenvector corresponding to lambda R n minus R, where n is the order of the matrix. This is the geometric multiplicity we all of us know, and we all of us know what is the algebraic multiplicity. Since geometric multiplicity means number of linearly independent eigenvector corresponding to eigenvalue lambda, so geometric multiplicity always less than equal to algebraic multiplicity. And when a matrix be diagonalizable? A matrix is diagonalizable when geometric multiplicity and algebraic multiplicity both are equal. That means a matrix A of order n is diagonalizable if it has n linearly independent eigenvector. Okay? OL. This is the very shortcut method to find is a matrix be diagonalizable or not. By geometric multiplicity and algebraic multiplicity, we can easily find is one matrix be diagonalizable or not. Okay? Let's see one example. Our first example, which had come CSIR NET June 2019 exam. The question is, which of the following matrices is not diagonalizable over the field R? Option 1, the matrix 2 0 1 0 3 0 0 0 2. Notice, since this matrix is upper triangular matrix, that means eigenvalue of upper triangular matrices is 2 2, 2, 3. And since here the eigenvalue are not distinct and algebraic multiplicity of the eigenvalue lambda equal to 2 here 2, now we have to find how many eigenvectors exist for the eigenvalue lambda equal to 2. We all of us know, for this we have to find geometric multiplicity for lambda equal to 2. For this, we all of us know geometric multiplicity means null space of A minus lambda I, and by this rank nullity theorem, this would be A minus rank of A minus lambda I. Since here lambda equal to 2, that means this would be, and order of the matrix A is 3, then this would be 3 minus rank of A minus 2i. That means we have to find rank of A minus 2i. Now apply A minus 2i in this matrix, then this matrix is reduces 0, 0, 1, 0, 1, 0, 0, 0. That means rank of A minus 2i is 2. And geometric multiplicity for lambda equal to 2 is, since rank of A minus 2i is 2, that means this would be 3 minus 2 equal to 1. Since algebraic multiplicity of lambda equal to 2 is 2, and here I have got geometric multiplicity is 1, that means algebraic multiplicity is not equal to geometric multiplicity. That means this given matrix is not diagonalizable. And here the question has indicated which of the following matrices is not diagonalizable overall. That means option 1 is a right option. Next, 2 cross 2 matrix 1, 1, 1. Then for this, at first we have to check the eigenvalue. At first we have to find the characteristic polynomial. That means we have to find determinant of A minus lambda I equal to 0. And from this equation we can tell the characteristic equation are lambda square minus 2 lambda minus 2. That means this imply from this equation lambda times lambda minus 2. That means lambda equal to 0 and lambda equal to 2 be the eigenvalue of this characteristic polynomial. And since both are distinct, so obviously the matrix A is diagonalizable. Next I will see this matrix 2, 1, 0, 0, 3, 0 and 0, 0, 3. Since here the upper triangular matrix, so obviously since here the eigenvalue are 2, 3, 3, so algebraic multiplicity of lambda equal to 3 is 2 and geometric multiplicity of lambda equal to 3 is obviously n minus rank of A minus 3i, and A minus 3i means minus 1, 1, 0, 0, 0, 0 and 0, 0, 0, and rank of A minus 3i obviously 1. So geometric multiplicity is here 2. That means since algebraic multiplicity of 3 is 2 and geometric multiplicity of 3 is 2, that means obviously A is diagonalizable, because geometric multiplicity here similar to algebraic multiplicity for lambda equal to 2 and other value, here lambda equal to 3 and other eigenvalue is obviously distinct. So option 3 is a right option. Now I will see the option 4. Here the characteristic polynomial is for this matrix lambda square minus 5 lambda plus 6. That means that imply lambda minus 2 times lambda minus 3 equal to 0. That means lambda equal to 2 and lambda equal to 3 be the eigenvalue. And since both eigenvalue are distinct, so obviously this matrix is diagonalizable. That means only option 1 is a right option, because in the question has given which of the following matrix is not diagonalizable over R. All other matrix 2, 3, 4 both are diagonalizable. Only option 1 is a wrong option. So only option 1 is a right option. Today I will stop here. In my next video, I will discuss this topic elaborately, because this is very important for any competitive exam. See you soon. Stay safe and stay positive always.